Okay, so what we're going to do here is I'm going to use the process we've been learning for several days here, and actually we've been building up this because we learned how to classify equations a week ago, and then learned to predict products. But predicting products, a lot of that is just stuff we learned in Unit 3 and 4. So we're really not learning a lot of new things. We're learning to put it together in a new way. So in order to figure out what kind of classification of equation it is, you got to look at the reactants. Well, I've got a compound that is, what kind of classification of compound is this? Well, there's a polyatomic ion here, but I want to know what the compound is. This compound. Is it ionic or covalent? Why is it ionic? A metal and a non-metal, so that makes it ionic. So we know we got an ionic compound, okay? All right, what kind of compound is this one right here? It contains a polyatomic ion, so what kind of compound is it? Ionic. So, if I have, those are the two ways you figure out if you have an ionic compound. If it has a metal bonded with a non-metal, in this class, you can assume it to be ionic. If it contains a polyatomic ion, in this class, you can assume it to be ionic. And if I have two ionic compounds that potentially could react together, what classification of equation is it? What? It is double replacement. An S. That's synthesis. Synthesis means you take two smaller things and make a bigger thing. But this is double replacement. Two ionic compounds, double replacement. Okay? Two ionic compounds, double replacement. So what happens in double replacement? Switch the front and backs. Okay? So the front part of this compound goes with the back of this one. We're not going to balance the compound yet. We're just going to, I'm sorry, I forgot to put a 2 here. We're going to just put this front part, potassium, with this back part, what's this called? Well, what is this part of it right here called? We said it's a polyatomic ion. What's its name? Nitrate. Okay, we're going to put the front part of the front one with the back part of the second one. But we're not going to balance the compound yet. This subscript does not travel over automatically. This subscript tells me I have 2 nitrates here. I don't know how many nitrates I need in this compound yet. Okay? The only subscripts that travel are those that are part of the polyatomic ion formula. And the only way you're going to know what the polyatomic ion formula is to do what? Look on the common ions list. It's there. Okay? And you'll find the name nitrate. You'll find out what the formula is. You'll find out what its charge is. Anytime you have more than 2 elements, one of the first things you want to do is look on that common ions list and see if you can identify a polyatomic ion in that formula. Yes? Yes. In this case, we have a metal and a non-metal. Any subscripts over here are not going to travel over automatically. Now, there aren't any here, but if there were some, then they would not travel over automatically. The only subscripts that travel automatically are those like this one that are actually part of the polyatomic ion formula. Okay? All right, now we've got to take the front part of this and put it with the back part of this. And you have to remember, front parts stay front parts. Okay? Just like you wouldn't put your shirt on your legs, and go to school, you don't put the front part in the back. All right? Magnesium then is going to go with fluorine. But we're not going to balance the formula yet. We're just going to stick them together. And the reason we're sticking them together is because the first thing we want to do after we do this is use this to figure out if there's a driving force. Now, there's 3 driving forces. You have to know about all 3, but you only have to know how to use 2 of those. One of those is the formation of water. And is there water over here anywhere? No. So we didn't form any water. That one's out. The only other driving force in this case that we have to worry about is the formation of a solid. So we need to know if this is a solid or this is a solid. Okay? And you use the solubility rules for that. Okay? I can loan you one until I can print one for you. All right. So let's look at this one right here first. Listen. If you're missing things in your knowledge base, in your little toolbox of knowledge, maybe you need to pay more attention on a daily basis. All right. This is a group 1 metal because it's in group 1, which is the first column of the periodic table. That's why we call it group 1. Okay? This is the polyatomic ion nitrate. We just said it was. We looked at it. We said you could look it up on the common ions list. So if I look in the solubility rules, I can see the very first solubility rule. It says both nitrates and group 1 salts, and this is a group 1 salt because it's an ionic compound with group 1 in it. They're soluble. Soluble means it can dissolve. It's aqueous if there's water around. And because these compounds say aqueous, you know there's water around. Okay? So this is going to be aqueous. Okay? Nitrates and group 1 salts are soluble. They will be aqueous if there's water around. The fact that these two compounds on this side of the equation say aqueous means they were dissolved in water, so water has to be there. So we're going to show this as being aqueous. All right. Now we're going to look over here at this one. Magnesium and fluorine. The fluorine ion is fluoride. It's a negative ion. Monoatomic ions with a negative charge are have an IDE ending. That you change the end of the name of the element to IDE. So that's fluoride. And we're going to look through the solubility rules, and I'll find fluorides right here. It says fluorides are soluble unless they're bonded with group 2. Where's magnesium? If you aren't using your periodic table and visually referencing this, you're practicing for failure. Because failure to practice is practicing to fail. Okay? The more you use your references and visually use them every time I talk about them, the more likely you are to be able to use them properly on a test. Okay? That's practice like everything else you do. So this fluoride, since most fluorides are soluble, but not if they're combined with group 1, and magnesium is group 1. So if it's not going to be soluble, it's going to be insoluble, and if it's a solid. Okay? Correct. So do we have a driving force? Yeah, because we formed a solid. All right? That's how you use the solubility rules. There are 3 driving forces. 3 driving forces. If it's a double replacement reaction, you have to look at the products. And if you form a gas or water or solid, that's a driving force. We are not going to have problems in this class that form gases. So the only ones you have to worry about for equations, you have to know about all 3. The only ones you have to be able to use like this are the formation of water or solid. Sure. Okay, well, let's finish this first. You got a question about this? Well, we haven't balanced it yet. You're absolutely right, but we hadn't gotten to the point where we're ready to balance it yet. We do have to balance the formulas, though. Okay? So what we want to do, Dalton, because if there's no driving force, there's no reason to do anything else, right? If there's no driving force, you're going to just mark it out and put in R. All right? But now that we've figured out there is a driving force, now we need to do all that other stuff. So, what is the charge on a potassium? 1 positive. And where did you find that, Jason? The periodic table that has oxidation numbers on it. You might also know that if it's in column 1, look at all those elements in column 1. They all have the same charge, plus 1. So if it's in column 1, that's a no-brainer. It's a 1 plus. Okay? What's the charge on the nitrate? Where do you find that? No, the polyatomic ions you find on the common ions list. Okay? So what charge do you put on a nitrate? A single negative. So that's already charge balanced. As many positive charges as negative charges, that formula is balanced. Okay? Let's go over here to magnesium and fluorine, or magnesium fluoride. What's the charge on magnesium? 2 plus. It's in column 2, and all the elements in column 2 have the same charge, 2 plus. How about fluorine? What's its charge going to have to be? A single negative. It's not 2 negative. Look on the periodic table with oxidation numbers. It says it's 1 negative. Now sometimes you have some elements that have positive charges and negative charges. If the front part's a metal, it's going to have to be positive. The back part has to be you have to choose a negative charge. Got to be. Okay? So how many of each of these do I need to be charge balanced? I need 2 fluorines, and so the formula, that's 3 separate ions here. When I bond them together like this, I need to use a subscript 2 to show I have 2 fluorines bonded with that magnesium. That's what the subscripts tell you. Things are bonded together. Okay? Let me put glue in there. You bond them together. I'm putting those subscripts in there. All right? So now the formulas are balanced. We're ready to balance the overall equation. Okay? So for that, we're going to use an atom inventory where we list all of our elements. And we make a grid so we keep everything nice and neat and keep up with all of it. And we're ready to count the elements we have. All right, we have our atoms. We have 1 atom represented here for this potassium, 1 fluorine, 1 magnesium. This 2 outside the parentheses means I have 2 nitrates. So everything inside the parentheses is multiplied by 2 in terms of counting atoms. So how many nitrogens do I have? And how many oxygens do I have? 6. Good. See, 3 in the nitrate times 2. Okay? Over here, how many potassiums on the right-hand side? 1. How many fluorines on the right-hand side? Subscript 2 means I have 2. How many magnesiums? 1. How many nitrogens? 1. How many oxygens? 3. Okay? Now, we want to balance oxygen last. You always balance oxygen last, and if there's a hydrogen, you do that next to last. There's no hydrogen here, but if it ever comes up. So we can start with fluorine. That's the first one up here. You don't have to. You can start anywhere else. Just don't do oxygen till last. So here's fluorine. I got 2 on the right. I want 2 on the left. Now, once the formulas are balanced, we balance these 2 formulas. We don't touch those. So leave them alone. Okay? Leave alone any formulas once they're balanced. You can only use coefficients in front of the formulas to balance the equation now. So I want to put a 2 in front of this formula to show I have 2 of these formula units in order to get 2 fluorines. I'm going to change, but by doing so, it's changing the number of potassiums and fluorine. Because I now have this formula unit had 1 potassium and 1 fluorine. I have 2 of them. I have 2 potassiums and 2 fluorines. 2 and 2. Huh? So now that I've done that, I've unbalanced the potassium. Well, let's go over here and put a 2 there. And that's going to change on this side of my atom inventory the potassiums, the nitrogens, and the oxygens. So 2 times the 1 I had originally, I have 1 potassium in the formula originally, times 2 is 2. I have 1 nitrogen to start with, times the 2 gives me 2. 3 oxygens is what I had to start with, times 2 gives me, and we're done. It's balanced. Or we're done balancing the equation. We still have to do, as far as this example is concerned, we're also going to write complete Ionic equations here. Okay? All right. So, in a complete Ionic equation, you split up into separate ions, ionic compounds that are aqueous, and only the ionic compounds that are aqueous. Okay? You don't split up covalent compounds, you only split up ionic compounds, and you only split up ionic compounds if they're aqueous. So I have 3 aqueous compounds, right here and here and here. Okay? Those are the ones we're going to split up into their separate ions. We kind of already did it here. Okay? We showed what this would be made of and we figured it out over here. Okay? So let's go back over here. This is undoing what you learned to do to balance compounds when you're in Unit 3. So we're just undoing what you already learned to do. Okay? So we have potassium, and we said the charge on the potassium is a 1 plus. And how many potassiums do I have? 2 of them. There's a coefficient 2, so I have 2 potassiums here. There's only 1 potassium in the formula unit, times that 2 means I have 2 potassium. Since the formula unit is aqueous, when you dissolve that in water, it splits up into separate ions, but those separate ions are still dissolved. So this ion is also aqueous. So here's our fluoride. It's also aqueous, and it has a 1 negative charge we said over here. And we have how many of those? 2 fluorines, or 2 fluorides, I should say. Because it's a monoatomic negatively charged ion, an anion, we name the end of it IDE. Alright, now this is aqueous. It's an ionic compound, we said, so we're going to split this up. We already said that magnesium has a 2 plus charge. If this is aqueous, the separate ions that break up into the water are aqueous. And then we've got how many nitrates? 2 nitrates. This coefficient 2, subscript 2 over here means I have 2 nitrates. And what's the charge on the nitrate? We already found it to be 1 negative. And so this is going to be aqueous. Alright? I've got potassium nitrate. It's aqueous. It's going to split up. And we've already written what the ions look like. Okay, we're going to have a potassium ion. And we're going to have a nitrate. The only thing is I've got 2 of that formula unit. Okay? 2 of that formula unit there. So that means I'm going to have 2 of each of these. Remember, we only split up the things that are both ionic and aqueous. This formula here is ionic, but it's not aqueous. We found it to be a solid. So if that one doesn't split up, we write just the way it looks up there. Okay? And there's a complete ionic equation. So, the net ionic equation then writes down in a new equation only those things that change. Not the things that stay the same, only the things that change are written in the net ionic equation. Okay? So we're looking at potassium here. I've got 2 potassium ions that are aqueous. That's exactly the same over here. I'm not going to write that down. What? There's the 2 fluorines. Those are fluoride ions. They're aqueous. They're separate. That's not the same thing as these 2 fluoride ions bonded together. Nor is it the same as being solid here. So that fluoride is going to be written down, and so is this. The magnesium also changes in the same way. I've got a 2 plus charge on this ion. It's aqueous. This magnesium is bonded together into a solid. Nitrate doesn't change. It's the same. The things that stay the same are called what? Spectators. Spectator ions. You need to know that. Ions that stay the same on both sides are called spectator ions. So potassiums here are spectator ions, and nitrates are spectator ions. All right. Ions that don't change are called spectator ions. It's a real simple definition. Ions that don't change are called spectator ions. Okay? They're not in the game. They're in the stands. They're not participating in the reaction. They're just sitting around. They might stand up and cheer sometimes, but they're not actually participating in the game. Alright, so fluorine we said is going to change. Magnesium we said is going to change. And then magnesium fluoride was changed from these. And that's the net ionic equation. Okay? I hope so. You may. Okay? Huh? Sure. We can do all that stuff as time allows. I'll do all those things. Okay. A combustion reaction for this class. Now, combustion reactions are much broader than we use them in here. But for this class, a combustion reaction will always start with a hydrocarbon fuel and atmospheric oxygen. combustion reaction will always start with a hydrocarbon fuel and atmospheric oxygen. And we dealt with those when we did the thermochemistry unit. We did that second so we could do the ice cream lab outside while it was still warm. Okay, so that was unit 10. We moved to basically the second unit we did. And we dealt with a lot of combustion reactions in there. Okay? So let's start with this one. And I'm going to let you guys work on that for a few minutes. Work with a neighbor. Work with a learning partner. What? That's FE, yes. All right, so because the double replacement products here, where sodium goes with nitrate, is aqueous, and because iron going with chloride is aqueous, there's no driving force. There's three driving forces in a double replacement reaction. They are the formation of a gas, the formation of water, and the formation of a solid. Now, we don't have any double replacement reactions in this class. No double replacement reactions in this class that will form gases. We do form water, and that will be a driving force, and we do form solids, that will be a driving force. But there's no driving force here because there's no solids or water or gas. So there's no reaction. That's all you have to do. Figure that out, put NR, and you're done. Go to the next problem. And the next problem here is this one. Okay? So we're going to determine if there's a driving force. If there is, then you're going to complete everything, okay? All right, so let's see how this works. Elements that are by themselves can only replace elements in a compound they are like. So halogens only replace other halogens. Metals only replace other metals. On your activity series, you've got a halogens list to show where halogens replace other halogens, and you've got a metals list to show where metals replace other metals. Since chlorine is a halogen, we know it's a halogen because it's in column 7A on the periodic table, also known as 17. These are halogens, okay? Halogens replace halogens, and metals, everything from the stair step this way, replace other metals. Okay? So this chlorine has to replace something it's like, has to replace another halogen if it will replace anything. So if it's going to replace anything, it's got to replace this iodine, which is also in column 7, or 7A. So now we've got to go to the activity series to see if it does or will replace iodine. Since chlorine is listed higher than iodine, then we can assume clearly that chlorine will replace iodine in the compound. So the chlorine will replace this, producing this. Chlorine will replace this, producing this. Okay? Chlorine will replace this, producing I2. Iodine is one of the 7 diatomic elements you must know from memory. Well, guess what? 4 of them are kind of listed for you. The other 3, besides these 4 diatomic elements, are hydrogen, nitrogen, and oxygen. They're all diatomic. This 4 and hydrogen, nitrogen, and oxygen are diatomic elements. You have to know the diatomic. All those 7 are also going to be considered in this class to be gases, except bromine. Bromine is considered a liquid. So, chlorine is going to displace iodine. We'll have iodine by itself. It's diatomic. it's a gas. Okay? Since chlorine displaces iodine, that means it's joining up with the sodium. So we put sodium and chlorine together. Subscripts do not travel over here unless they're part of a polyatomic ion. This is not a polyatomic ion. It's a molecule. Polyatomic ions have charges. Okay, you can find those on your common ions list. This ain't one of those. Okay? I know that's not proper English, but we're in the South. Okay. So we need to know the charges on the sodium and chlorine to balance it. Sodium has a 1 plus charge. Chlorine has a 1 negative charge. So I've got as many positive charges as negative charges without any subscripts. So that's a balanced formula. We need to know whether it's a gas. I mean, that's going to be aqueous because we've got water around here. This compound is aqueous, meaning there's water there that dissolved it. So if this is also soluble, it will be aqueous. And it says that all group 1 salts are soluble. So that means if there's water around, it will be aqueous. It also says that chlorides are all soluble. There's some exceptions, but sodium's not one of them. So this is aqueous. So we have the formulas balanced. We have the physical states identified. We're ready now to do an atom inventory to balance the equation. So we're listing all the elements. We're making a kind of grid to carefully count all the atoms to make sure we have the same number of atoms on both sides so that our work will obey the law of conservation of mass. So we have 1 sodium, 1 iodine, 2 chlorines, 1 sodium over here, 2 iodines, and 1 chlorine. We want the numbers to be exactly the same on both sides. Right now I can see I've got 1 iodine here and 2 here. Once the formulas are balanced, can't touch this. You have to figure out how to balance the overall equation using only coefficients. You don't change the formula, but you can have more than one formula. That's going to give me 2 chlorines, but it's also going to change the number of sodiums. Okay, this 2 means I multiply everything, so I've got 2 sodiums now and 2 chlorines. Now that I've unbalanced the sodiums here, I want to go back and balance the sodium. So I need a coefficient 2. That's going to give me 2 sodiums and 2 iodines, and that's going to balance the equation. Now we're ready to write the complete ionic equation. Okay, so the only things we break up in a complete ionic equation are those aqueous ionic compounds. That's the only ones we break up, aqueous ionic compounds. This is aqueous, and we know it's ionic because it has a metal bonded with a nonmetal. This is aqueous. We know it's ionic because it's a metal bonded with a nonmetal. So we're going to break it up into the separate ions we used in Unit 3 to make it in the first place. We already showed how this breaks up. What we're trying to do is figure out how we would have formed this compound back in Unit 3. We would have formed it from a sodium ion and an iodide ion. We know sodium is 1 plus. We know the ion is going to be aqueous because if the compound's dissolved in water, it dissolved because it broke up. So the ions have to be in aqueous as well. The 2 means I have 2 sodiums and 2 iodides. So you're going to find those charges on the periodic table with oxidation numbers. Okay, in this class, you're allowed to use this test reference, and it has all the possible, or actually the most common, oxidation numbers. And sodium has a 1 plus charge. Since sodium is positive, chlorine has to be negative, and the only negative charge on the chlorine is a 1 negative. That's where we got those charges from. Iodine is also 1 negative here. Okay? Alright, so then chlorine, we said, is not ionic. It's not aqueous, so we have to just keep it together, just the way it shows it being here, a diatomic element. This is going to split up into 2 sodiums. Show a charge on the sodium and the chlorine, but not the iodine.
But not when they're not when they're not split up.
Right, right. So the iodine doesn't change because it's not ionic and it's not aqueous. Has to be both to split it up. All right, so that's the complete ionic equation. Now, to write the net ionic equation, all we're going to do is to get rid of anything that stays the same. If it's not changing, it's called a spectator ion. And sodium is exactly the same on both sides. It's a spectator ion. Iodine changes from an ion with a charge that's aqueous into a molecule that's a gas. So it's going to change. Chlorine goes from being a molecule into two separate ions. So those are the things that change. We keep those, but we don't keep the sodium. Oh, gas, not a solid, gas. All right, so there's your net ionic equation. All right? Now it's important to remember that you can figure out if you have a driving force for a single replacement reaction before you ever write the products. Because if the element by itself is more active than the element it is like in the compound, you will have a driving force. For double replacement reactions, you've got to figure out what the products are going to be before you can figure out, or part of what the products are going to be, before you can figure out whether you have a driving force. For double replacement reactions like this one, you don't know if it's going to be a reaction or not until you see how the products go together over here and then figure out if you have a water or you have a solid in this class. Okay? We don't have to worry about, in this class, we don't have to worry about determining if gases are formed. Okay? All right, does everybody follow me okay here so far? All right, then. You want to do more? You got other questions you want me to cover? Okay, we can do more. Yes, you can use the restroom. You also may use the restroom. All right, we're going to step it up a notch here. All right. So here's the problem that I'm assigning for you to do as a class in preparation for tomorrow's test. Yes. What? Okay, good.